Hello everyone, and welcome back to the channel. Have you ever wondered why you shiver when it's cold, or sweat when it's hot? Or what those numbers on the thermometer actually mean? We talk about temperature every single day. It's boiling out there. Or it's freezing. But what exactly is temperature? It's so much more than just a number for the weather forecast. Today, we're diving deep into the fascinating world of temperature. We'll explore what it is at a microscopic level, how we measure it, and how it impacts absolutely everything around us, from the tiniest atoms to the vastness of space. We'll even look at some of the most extreme temperatures in the universe. So, grab a comfy seat, maybe a hot or cold drink, depending on your preference. And let's unravel the science behind what makes our world hot, cold, and everything in between. So, what is temperature, really? On a fundamental level, it's all about motion. Everything in the universe, from the air you're breathing to the chair you're sitting on, is made of tiny particles like atoms and molecules. And these particles are never perfectly still. They're constantly wiggling, vibrating, and zipping around. Temperature is simply a measure of the average kinetic energy, or the energy of motion of these particles. When you heat something up, you're giving its particles more energy, causing them to move faster and faster. When you cool something down, you're taking energy away, and the particles slow down. It's like a microscopic dance party, and temperature is the DJ controlling the tempo. A hot object has particles dancing wildly, while a cold object has them doing a slow, gentle sway. To measure this dance, we use thermometers. But how do they work? Most common thermometers, like the old-school ones with the red or silver line, use a principle called thermal expansion. When the liquid inside the thermometer, usually alcohol or a mercury substitute, gets warmer, its particles move faster and spread out, causing the liquid to expand and rise up the narrow tube. When it gets colder, the liquid contracts and falls. It's a clever way to make the invisible motion of particles visible to us. Of course, we have different scales to put a number on it. In the United States, we mostly use Fahrenheit, where water freezes at 32 degrees and boils at 212. Most of the rest of the world uses Celsius, a much simpler scale where water freezes at 0 and boils at 100. It makes a lot of scientific sense, but in the world of science, the king of temperature scales is Kelvin. The Kelvin scale is based on the idea of absolute zero. What is absolute zero? It's the coldest possible temperature that can theoretically be reached. It's 0 Kelvin, which is equivalent to minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. At absolute zero, particles would have the minimum possible kinetic energy. They would essentially stop moving altogether. It's a mind-bending concept, a state of perfect stillness. While scientists have gotten incredibly close, reaching temperatures just fractions of a degree above absolute zero in labs, reaching absolute zero itself is thought to be impossible. It's like a cosmic speed limit, but for cold. Now, let's talk about heat, because you can't discuss temperature without it. Heat is the transfer of thermal energy from a hotter object to a colder one. This happens in three main ways: conduction, convection, and radiation. Conduction is heat transfer through direct contact. Think of a metal spoon in a hot cup of tea. The heat from the tea makes the particles in the spoon vibrate faster. And that vibration travels up the handle until you feel it. Convection is heat transfer through the movement of fluids, like liquids or gases. When you boil a pot of water, the water at the bottom gets hot, becomes less dense, and as the cooler, denser water at the top sinks to take its place, gets heated, and rises too. This creates a circular flow, a convection current, that distributes heat throughout the pot. This is also how weather systems work in our atmosphere. The third way is radiation. Unlike the other two, radiation doesn't need any matter to travel. It's the transfer of heat through electromagnetic waves. 2. The most obvious example is the sun. We feel the sun's warmth even though there's a vast, empty vacuum of space between us. The sun radiates heat across millions of kilometers, and when that radiation hits your skin, it transfers energy and makes you feel warm. A campfire also warms you up through radiation. Temperature is crucial for life as we know it. Our bodies, for example, are incredibly fine-tuned to maintain a stable internal temperature of around 98.6 degrees Fahrenheit, or 37 degrees Celsius. This is called homeostasis. If our body temperature rises even a few degrees, we get a fever. And our enzymes, the proteins that carry out all the chemical reactions in our cells, can start to break down. If it drops too low, we risk hypothermia. 3. Shiver to generate heat through muscle contractions, and we sweat to cool down through evaporation. Our bodies are amazing temperature-regulating machines. Temperature also dictates the states of matter. Take water, HO below 0 degrees Celsius. Its molecules lock into a rigid crystal structure, and we get solid ice. Between 0 and 100 degrees, the molecules have enough energy to slide past each other, giving us liquid water. Above 100 degrees, the molecules have so much energy that they break free and fly around as a gas, which we call steam or water vapor. This is true for almost every substance, each with its own unique freezing and boiling points. Let's zoom out and look at the cosmic scale. Temperatures in the universe are extreme. The surface of our sun is a scorching 5,500 degrees Celsius. But its core, a staggering 15 million degrees Celsius. That's hot enough to fuse hydrogen atoms together, creating the energy that powers our entire solar system. On the other end of the spectrum, the vacuum of deep space is incredibly cold, just about 2.7 Kelvin, or minus 270 degrees Celsius. This isn't absolute zero because of the faint afterglow of the Big Bang, the cosmic microwave background radiation, which permeates all of space with a tiny bit of warmth. The hottest temperature ever recorded in a lab was at the Large Hadron Collider, where scientists smashed gold ions together to recreate the conditions just after the Big Bang. They created a quark-gluon plasma that reached a temperature of about 5.5 trillion degrees Celsius. That's trillions, with a T. It's a number so large it's almost impossible to comprehend. So, from the shivering of your body to the fusion in the heart of a star, temperature is a fundamental force that shapes our reality. It's the invisible dance of atoms that determines whether something is solid, liquid, or gas, whether life can thrive, or whether a star will shine. The next time you check the weather, or feel the warmth of the sun on your face, or even just make a cup of tea, take a moment to appreciate the incredible, complex physics of temperature at play. It's one of the most basic, yet most profound, concepts in all of science. Thank you so much for joining me on this journey from absolute zero to the heart of a star. I hope you found it as cool or as hot as I did. If you enjoyed this video and learned something new, please give it a thumbs up and consider subscribing for more deep dives into the wonders of science. Let me know in the comments what scientific mystery you'd like us to explore next. Until then, stay curious.